guys, welcome back. Nice to see everyone again. And we are moving into the last subtopic of topic 7.3, intermolecular forces. And in this part of video, we'll talk about van der Waals forces and also hydrogen bond. What is actually intermolecular forces? Intermolecular forces is the attractive forces between molecules. So if I have a water molecule over here, one water molecule, and then I have another water molecule. So between this water molecule, we have some forces that hold them together that we call intermolecular forces. So bear that in mind, intermolecular forces must be sitting between molecules. What you have learned previously is called covalent bond, and this is your covalent bond. So covalent bond is between atom and atom to form one molecule. Intermolecular forces is between molecule and molecule. So make sure you can differentiate covalent bond and also intermolecular forces. And obviously, intermolecular forces is much weaker compared to your covalent bond. Covalent bond is the bonding form between the atoms in a molecule. So that is much stronger. Compared to the intermolecular forces, is the attractive forces between the molecule. So bear that in mind, it must be between molecule. And intermolecular forces will be affecting or it will determine the physical properties such as melting point, boiling point, or solubility. Generally, we have two types of intermolecular forces. Intermolecular forces can be separated into van der Waals forces and also hydrogen bonding. And we have two different types of van der Waals forces. First and foremost, dipole-dipole forces. Second, we can have London forces. So dipole-dipole forces and London forces both are under van der Waals forces. So let's look into detail of each and every one of these forces. First and foremost, let's look into dipole-dipole interaction, or we call dipole-dipole forces. Or we have another name of it that is called permanent dipole interaction. So this dipole-dipole interaction must happen to a polar molecule. Polar molecule means you are going to have a partially positive and a partially negative end, as you have learned previously on how to determine whether the molecule is polar or non-polar. And because of the partially positive and negative end, therefore you are creating a permanent dipole. And this permanent dipole will cause your dipole-dipole forces become very strong. So in a beaker that's full of a polar molecule, you can see a partially positive and a partially negative end. So you will have attractive forces between the partially negative and the partially positive. So these forces that is attracted between the partially positive and negative is what we call dipole-dipole forces. And they are permanent. Why are they permanent? Because the molecule itself from the beginning is a polar molecule. So you were forever in the stage of partially positive and partially negative. That's why the dipole-dipole forces is also called as a permanent dipole forces. Okay? Your dipole-dipole interaction will be highly affected by the polarity of a molecule. So, the higher the polarity, the stronger the forces. Bear that in mind, the polarity is affected by the electronegativity. So, the higher the electronegativity difference, the higher the polarity, the stronger the dipole-dipole forces. The another van der Waals forces will be your London forces. London forces is also called as dispersion forces. And London forces is actually exist in all molecules. London forces is like the most basic intermolecular forces that were present in all type of molecule. So in the other words, it will exist in your polar molecule. It will also exist in your non-polar molecule. But because in your polar molecule, you have a most significant forces, which is dipole-dipole forces. Alright, so in your polar molecule, you will have your London forces, you will have your dipole-dipole forces. But because dipole-dipole forces is more significant there, therefore, in the polar molecule, we will always discuss only about dipole-dipole forces. Therefore, in the non-polar molecule, you were not having the partially positive or the partially negative because it's a non-polar. So the electron negativity between the atom in the molecule are very similar. That's why it becomes a non-polar. And since you don't have the partially positive and partially negative end, therefore, you will only form a temporarily dipole. Temporarily dipole means what? Let's look into how London forces is actually formed. So the first condition for the London forces to happen is all the molecules must be close enough to each other. And if you look at all my negative charge over here, all my negative charge are evenly distributed in a molecule. Why? Because it's a non-polar molecule. So in a non-polar molecule, all the electrons will be evenly distributed. That's why you don't have a partially positive and partially negative end. There will be no one holding more electron or less electron. All the electrons will be equally distributed or evenly distributed. But we know that electron is something that will be keep moving around. And when the electron keep moving around, there will be at this one point where the electron in one molecule tend to move towards the same side. So when all the electron is moved towards one side, you will then cause a partially positive and a partially negative end. But this partially positive and negative is temporarily dipole. It's not going to last long because there is only one moment where the electron is all moving towards the same side. So you will cause a temporarily dipole, a temporarily partially positive and partially negative. But because all the molecules are right now close enough to each other, so this partially positive and the partially negative end will be affecting the neighboring molecule. So the neighboring molecule over here will be affected by this negative charge. All the electron will be moving away from this negative end. So all the electron will then move towards one side. And this will then cause again a partially positive and a partially negative. Same thing over here, it will be affecting the neighboring molecule. You have a partially negative end over here. So what happened to all the electron? All the electron will be then moving to one side. And you cause a partially negative, partially positive end. And eventually, it will be affecting all the neighboring molecule in the beaker. So what happened is all because of, it started from one molecule forming a temporarily dipole of partially positive and negative. And then, if the molecule is close enough to each other, it will be then affecting the neighboring molecule. So the electron in the neighboring molecule will be then repelled from the partially negative. Bear that in mind, all the electron is holding negative charge, so they will repel each other. And when you form a temporarily positive and temporarily partially negative, you will then form a London forces, or we call a dispersion forces. And this dispersion or London forces will be formed in a temporarily dipole condition where the molecule must be close enough to each other. Simple. And that is what we call London forces or dispersion forces. The main difference between the dipole-dipole forces and the London forces is the polar molecule and the non-polar molecule. The temporarily dipole and the permanent dipole. Think about that. Okay? And the London forces will be affecting by two factors. First, size of the molecule. Second, shape of the molecule. The size of the molecule, or we call it the molar mass, or called polarizability, is all about the size or the molar mass. The bigger the size or the higher the molar mass, the London forces will be stronger. Okay? How about the shape? Shape, we will be talking about contact surface area. So the larger the contact surface area, the stronger the London forces. So London forces will be affected by the molar mass or the contact surface area of the molecule. So the higher the molar mass, the stronger the van der Waals forces. The higher the contact surface area, the stronger the van der Waals forces. As a conclusion, van der Waals forces is highly affected by three factors. The first is molar mass. The first thing that you do is you always check the molar mass. The higher the molar mass, alright, the stronger the van der Waals forces. So the first thing that we always check is the molar mass. Calculate the molar mass first. If the molar mass is the same, if the molar mass is now the same, then only you check the molecular shape. Molecular shape is about contact surface area. So the higher the contact surface area, the higher the van der Waals forces. Alright? And we will only look into the molecular shape if the molar mass is the same or similar. If not, the molar mass itself already can determine who has a stronger van der Waals forces without looking into the shape. Last but not least is the polarity. We will only check the polarity if the molar mass is similar, the molecular shape is similar, then only we can check the polarity. With a condition, two above cannot differentiate that. Then only you look at polarity. So polarity over here, obviously, dipole-dipole forces is stronger than London forces. In the other words, polar molecule is having stronger van der Waals forces compared to your London forces. But with one condition, the molar mass is the same, the molecular shape is the same, then only you look at the polarity. So, van der Waals forces is actually highly affected by molar mass. The first thing that you do when you realize both of them or all your molecules are having van der Waals forces is to check the molar mass to determine who have a stronger van der Waals forces. Make sense? Next, let's go into hydrogen bond. Hydrogen bond is the strong permanent dipole forces between molecules. Same thing, we are still talking about between molecules. But what makes hydrogen bond different from dipole-dipole forces, or what makes hydrogen bond so strong? Why am I having a strong permanent dipole over here? Because of the electronegativity. Your hydrogen can be formed between the molecule that have these two criteria. The hydrogen atom covalently bonded to fluorine, oxygen, or nitrogen. For example, water molecule. So that is the covalent bond between the hydrogen and also the fluorine, oxygen, or nitrogen. It will then form the hydrogen bond, the attractive forces, with the electronegative atom, fluorine, oxygen, or nitrogen with at least one lone pair. Let's look at this. What is meant by this hydrogen bond? The example that I can give over here is water molecule just now. So you have a water molecule. You know that in your Lewis structure, your water molecule is a V shape with two lone pair at oxygen. That is how your water molecule look like. So you can see over here, that is my covalent bond. So my hydrogen bond can be formed from this covalently bonded hydrogen atom to an electronegative atom between F, O, or N with at least one lone pair. So the red color dot that I give to you between the H and the O over here is what we call hydrogen bond. And this hydrogen bond is formed between the hydrogen atom covalently bonded, that is my covalently bonded, to an electronegative with at least one lone pair. See that? That is what we mean by hydrogen bond. I can show you another example over here. For example, I have ammonia. Your ammonia looks something like this. I have another ammonia over here. So you can see that this is your covalent bond. Covalent bond between nitrogen and also hydrogen. Hydrogen bond covalently bonded to F, O, or N. That is your covalent bond. So this hydrogen will be forming a hydrogen bond with an electronegative F, O, or N with at least one lone pair. So that is my F, O, or N with at least one lone pair. and that is your hydrogen bond. Make sense? Okay. One more last example. You have your H and F hydrogen fluoride. You can see over here, your hydrogen is now covalent bonded to your F. Okay, so that this is your covalent bond. And you have another HF molecule. It's a 2 molecule over here. And the hydrogen will be formed between this hydrogen to the F atom. So you have one molecule, you have another molecule, and that is your hydrogen bond. So the condition for hydrogen bond is the hydrogen atom must be covalently bonded with FO or N, and then the hydrogen will form attractive forces to the electronegative atom FO or N that holding at least one lone pair. That is what we call hydrogen bond. So hydrogen bond can only be formed between the fluorine, oxygen, and nitrogen. So hydrogen bond can only be formed when you have a hydrogen covalently bonded to F or O or N. That is your basic requirement for hydrogen bond, and then you will form attractive forces with the FO or N that has at least one lone pair. That is your hydrogen bond. And your hydrogen bond is highly affected by the electronegativity. So why is your hydrogen bond become a strong permanent dipole? Because your F, O, and N, all three of these atoms is the highest electronegativity atom in your periodic table. Where from FO and N, the electronegativity decrease. In the other words, fluorine having the highest electronegativity, followed by oxygen, followed by nitrogen. This three is the highest electronegativity atom in your periodic table. That's why your hydrogen bond can form a strong permanent dipole, because it's between the hydrogen, the most electropositive atom, with the most electronegative atom, fluorine, oxygen, or nitrogen. And that causes your hydrogen bond to be very strong. The second factor affecting hydrogen bond is the number of hydrogen bond that your molecule can form. Okay? For example, I have HF and also I have H2O. Obviously, HF over here having higher electronegativity because fluorine is more electronegative than oxygen. So oxygen straight away having lower electronegativity. But the number of hydrogen bond that can be formed in HF is less compared to water. Water can form more hydrogen bond. And because of this, the boiling point of HF will be lower than the boiling point of H2O. Why? Because HF can form less hydrogen bond, so less energy is needed to overcome the hydrogen bond. Therefore, boiling point of HF is lower, but boiling point of H2O is higher. Because in water, there is more hydrogen bond, more energy is needed to overcome the more hydrogen bond. Okay, simple. As a conclusion over here, hydrogen bond is much stronger than van der Waals forces. In the other words, boiling point in hydrogen bond will definitely be higher than the boiling point in the van der Waals forces, because more energy is required to overcome the strong hydrogen bond compared to van der Waals forces. So those molecules that can form hydrogen bond will definitely need more energy and having higher boiling point. Those molecules that only have weak van der Waals forces will have a lower boiling point and only require small amount of energy to overcome the van der Waals forces. Example of molecule that can have hydrogen bond is like your HF, your H2O, your ammonia is among the molecule that can have hydrogen bond. While for your van der Waals forces, it could be like Cl2, Br2, you can have your HCl, HBr, your CH4, your CH2, Cl2, CCl4, and a lot more. All of this is actually your van der Waals forces, okay? whether it's London forces or whether it's dipole-dipole forces, they are all under van der Waals forces. Okay? Like we have talked about just now, intermolecular forces will be highly affecting your physical property. One of the physical property that you will always learn is boiling point. So the stronger the intermolecular forces, the higher the boiling point. Why the stronger the intermolecular forces, the higher the boiling point? Because more energy is needed to overcome strong intermolecular forces. So the stronger the intermolecular forces, the higher the boiling point because you need more energy to overcome it. How can we predict the boiling point of a list of molecules? If the question gives you a few molecules, how do I know whether which one have a higher boiling point, which one have a lower boiling point? Simple. First and foremost, you need to predict the intermolecular forces. And we have two intermolecular forces, your hydrogen bond or your van der Waals forces. And obviously, the one that having your hydrogen bond will have a higher boiling point straight away. The one that having your van der Waals forces will have a lower boiling point straight away because hydrogen bond is stronger than van der Waals forces. How about if both of them are hydrogen bond? If all of your molecule is hydrogen bond, what do? We are going to check electronegativity and the number of hydrogen bond. Electronegativity is your F, O, and N. So we know that electronegativity over here decrease when you are moving from fluorine to oxygen to nitrogen. Next that you need to check also is the number of hydrogen bond. The higher the number of hydrogen bond, the higher the boiling point. So the example that I give to you just now is H2O and HF. So H2O can form more hydrogen bond compared to HF. That is how we check which one will have higher boiling point. And how about everything right now is in van der Waals forces? All the molecules are having van der Waals forces. So van der Waals forces affected by three things. First and foremost, affected by molecular mass. The higher the molecular mass, the higher the boiling point. So the molecular mass is the first thing that you check when you have a list of van der Waals forces molecule. The one that having higher molecular mass will straight away become higher boiling point. If the molar mass is the same, then we will be checking the molecular shape, or we call contact surface area. The larger the contact surface area, the higher the boiling point. So when the contact surface area is bigger, therefore the boiling point is higher. And next, if the molecular shape again is the same, then only we check the molecular polarity. Then we check the polarity. Obviously, in the polarity, dipole forces is stronger than London forces. So we are not checking the polarity at the beginning. Bear that in mind, van der Waals forces is highly affected by the molar mass. Therefore, the first thing that you check is the molecular mass. If the molecular mass is the same, then only you check the molecular shape. If the molecular shape is the same, then only you check the polarity. So that is how we predict the boiling point in a question that have a few molecules. First and foremost, we will definitely need to identify your molecule holding what type of intermolecular forces. Therefore, before we end this video, first and foremost things that you need to know is knowing that molecule having hydrogen bond or van der Waals forces. Go and figure that out. Bear that in mind, hydrogen bond can only be formed between hydrogen and F, O, and also N. So it's quite easy to actually indicate who is having hydrogen bond or not. Okay? And that's it for this video. So I hope in this video, it helps you to understand more about intermolecular forces and also the factor affecting the intermolecular forces, what will cause the hydrogen bond to be stronger and what will cause van der Waals forces to be stronger. And if you think this video helps you, do give me a like and do give me feedback or comments in the comment below. And don't forget to subscribe to my channel and I'll see you in the next video. Thank you.